Discontinuities and one-sided limits. A discontinuity is where components of an equation are not connected to each other. I've got some discontinuities right here to right here, and right here to right here. And notice I have some holes. That means it can, as it approaches -1 from the left, it is 2. But as it approaches -1 from the right, it is at -3 here. But the important thing to understand is these are discontinuities. The line is not continuous where I got my arrows pointing here. There are different types of discontinuities. The most common one is the removable discontinuity. And now I'll show you in a couple slides. That's basically, I have a hole right here, and I remove that point and put it up here. We're looking at some of those in earlier sessions. That is a removable discontinuity. I removed it, and I've put the point somewhere else. There's also, look at the previous slide, a jump discontinuity. There's a limit going to each side, but they have different values, so that's why it's not a normal limit. Infinite discontinuities. Another name for this is an asymptote. It can never be at that, so it is, but also considered in terms of limits, an asymptote. T-O-T-E. My writing is just terrible on this, and I apologize. Oh, now I'm making it worse. I was erasing. So, that is an asymptote. Endpoint discontinuities, only one side exists, but not the other, because we have a line that does this, and there's nothing on the other end. So that is endpoint discontinuity. And then mixed discontinuities is one of the one-side limits does not exist. And that's where I could have like a hole right here, it does not exist. Now, here's a removal discontinuity. Here it is, I've just removed it right here. There's just nothing there at the at 3, 10, little hole right there. And I can put it right back, as you can see right here. This is simply just called a removable discontinuity. I removed it from the line. It can be anywhere but at 3. Here's a jump discontinuity. As my x approaches 1, I have 2 points that are y right here. One's at 6, one's at 4. This is a jump. It's jumping from one to the other. Which one should it be? Actually, this goes back into the second week when we're talking about what makes a function. This one x goes to 2 y's. We know that cannot exist. So this is called a jump discontinuity. Infinite discontinuities. Both sides have the base and asymptote. It will never, in this case, it'll never approach 3. It closer to 3, but it can never be 3, even from both sides. And a mixed discontinuity. We've talked about these before. At least one side does not exist, as we got right here. Not only do we have a jump here, we also have a hole right here. And this is the endpoint discontinuity. Notice that the only point when I have x equals 1 right here, from the left it approaches 4, but it doesn't exist from the right because that hole means it doesn't exist. And you might see that sometimes as D, N, E, does not exist. Now we can have one-sided limits when we have discontinuities, but we have to express first that they are one-sided limits. Now, in this equation right here, 3x plus 1 equals x. Obviously, x can never be 0. So not only do we have an asymptote here, This isn't. This is a discontinuity, infinite discontinuity, because it's never be one. It can approach. I mean, never be zero. You get closer and closer to zero. But notice from the right, as x approaches 0, y becomes infinite. But from I said from right, from the left, as x. Let me rephrase that. From the left, as it approaches 0, it becomes infinity. So, and that's how I'd write this right here. As x approaches from the left, and this little minus here means approaching from the left, not minus, but it means x approaching 0 from the left, and that will actually equal infinity. As x approaches 0 from the right, and closer and closer to 0, it actually goes to negative infinity. So notice this is going in two different directions. But I've stated the limit from the left, where there's a minus, and from the right, which is a plus. Now let's see. Once that limits, we have discontinuities. Let's take a look at this. And what I have here is I have a series of equations. X squared plus 3 from negative 3 to 3. That's this right here. F of x equals 13 and x equals 7. Well, let's see. Here is 7 and there's 13. So this is 7, 13. And f of x was 15 from x equals 3 to x equals 9, but x cannot equal 7, which is what this is right here. So let's see how we could write these. So as x approaches 3 from the left, right here, this is 3. From the left, and I got from the left, f of x equals 12. As x approaches 3, right here, from the right, it equals 18. And also say from the right here. As x approaches 7 from the left, that'd be from over here. Nope, I take that back. It's approaching right here. It's not added, but it's approaching 22 from the left, approaching 22 from the right. So this is 8, and it goes to 22. And notice I'm not saying where it's at right here, but where it's approaching. So from the left and from the right at 9. One more here. What I have here is another set of 3 equations. Negative x cubed plus 4x plus 5 from 0 to less than equal to 0 is less than equal to x, less than equal to 1. That's this little part right here. And then negative 2x right here, negative 2. If x is negative 2 right here, there's negative 2 from 1 to 5. And then x minus 5 squared from 5 to 8. From 5 to 8. Notice I have a hole here, and I have a hole here. So let me erase my little scribbles here. And let's take a look at this. We have very difficult to talk to list, but regular list. We have one side of this. X approaches 1 from the left. This is from the left. Here's my 1. F of x equals 0. As x approaches 1 from the right, f of x equals negative 2. And notice I've got my 1 from the left with the negative, 1 from the right is positive. X approaches 5 from the left. Let's take a look at this. Here's 5 from the left. It equals negative 2. It's a straight line here. X approaches 9 from the right, let me see, no, that should be 5 from the right. X approaches 0 right there.